First thing that we need to know about differentiation is that differentiation is all about gradients. Now, we know how to calculate gradients, especially gradients of straight lines. For example, say you had a simple straight line that passes through the points 3, 3 and 6, 4. That gives a straight line that looks like that. To calculate the gradient of this line, we use the rule m equals the change in height over the change in width. That could be better written as y2 minus y1 over x2 minus x1, where x1, y1 is your point on the left, and x2, y2 is your point on the right. In this case, y2 is 4 and y1 is 3 over the change in x, so that is 6 minus 3, which gives us a gradient of 1/3. Now it's really easy to find the gradient of a straight line because we could pick any 2 points on the straight line and it will always be the same change in y over change in x. Now differentiation is about how can we take this idea and apply it to curved lines. I.e., if we had a curve, and our most basic curve is a quadratic, so we'll just use that as an example. If we had a quadratic like that, how could we find the gradient at any point? Because as the curve changes, the gradient of each point changes. So for example, we're going to draw a tangent. A tangent is a straight line that just touches the curve at one point, and so it would give us the gradient of that curve at that point. And this changes as we go along the curve. For example, there. Or there. And so because the gradient is changing, we now need a function that will tell us what the gradient will be at any point, instead of from the straight line, just a constant. So how do we do that? Because the issue we have right now is that we want to find the gradient at any one point, except just from before we saw that we needed 2 points to find a gradient. To see how we might find the gradient at only 1 point, we'll start with a curve. Any curve will do. I'm going to draw just a simple one that does that. And I'm going to start at the point A and point B. What I'm going to do is draw a straight line between them and try and calculate the gradient of that line. Now this blue line is called a secant line. Now this blue line isn't the tangent at A, and it's not the tangent at B either. It's somewhere in between. Our goal is to have this so B becomes so close to A. If I zoom in and bring B all the way down until it gets right beside it. It's not at A, but it's really, really, really close. Now if I draw a line between these two, I get something that looks a lot more like a tangent line. technically it's not because it goes through 2 points, but because these 2 points are so close together that it's sort of the same. If we then found the gradient of this line, where we got the points so close together, then we could sort of say, well, yeah, that's the gradient of the tangent at that point. We can't make it so A and B are the same, because if we did that, the change in x would then be 0. And if we look at our gradient formula, if the change in x is 0, we get a divide by 0, which you're not allowed to do. So to put this into practice, we'll draw one more graph. Now I'll copy the graph from before, sort of like that. And now I'm going to label some slightly different things. This will be x, and I'm going to define the next point here as being a step h away from x. So this distance here is h. It's a fixed value, which means this x value is x plus h. Now if this is the function y equals the function of x, then the y value at x would just be the function at x, and the y value at x plus h would be the function at x plus h. So I'm going to start by writing down the equation of the gradient of the secant line that goes between these 2 points. So gradient m equals the change in y, so that's the function at x plus h, minus the function at x, all divided by the change in x. Now we actually define the change in x as h, so over h. And what we want to do is bring h, so it's so close to 0, so small, that this point here travels down our line until it reaches a point so infinitely close to x. We want to see what happens as h becomes really close to 0. How we write that mathematically is, well, we start to introduce the differentiation form, so f dash x equals, and I want to see what happens as h approaches 0. Not when it's at 0, but when it gets really close to 0. The way we write that in maths is we want to find the limit as h approaches 0. A limit is simply what a function behaves like as you get really close to something, not when you're at it, but really close. Of fx plus h minus function of x over h. This here is the definition of differentiation. And we're going to use it to differentiate by what's called first principles, which is differentiating without any differentiation rules apart from rise over run. For example, say we had a function is x squared plus 4x plus 3. I want to find what the function of x plus h is, so then I can substitute this into our formula. To do that, all I'm going to do is wherever there's an x, I'm going to change it to x plus h. So x plus h squared plus 4x plus h plus 3. I'm then going to expand this. That will give me x squared plus 2hx plus h squared plus 4x plus 4h plus 3. I'm then going to substitute these two things into our formula. So function f dash x equals the limit as h approaches 0 of x squared plus 2hx plus h squared plus 4x plus 4h plus 3 minus x squared plus 4x plus 3. Now be careful, I'll put that in brackets because I'm subtracting the whole thing. All of that is divided by h. Simplifying, the x squared will cancel with the x squared, the 4x will subtract with the 4x, and the 3 will subtract with the 3. And that leaves us with 2hx plus h squared plus 4h over h. Now there's a common factor of h that can be cancelled. So we get the limit as h approaches 0 of 2x plus h plus 4. And at this point here, I'm going to see what happens as h gets really close to 0. Well, when that happens, this h term effectively goes away, and we're left with f dash x equals 2x plus 4. So in practice, we're just making h 0. You can't make h 0 at the previous step, this step here, because when we do that, I get a divide by 0. So you've got to work these questions through so you no longer have a divide by 0 when you make h 0 and then make h 0. A slightly more complicated example would be to differentiate y equals 2x cubed plus x. I find the gradient at any x point. So the function of x equals 2x cubed plus x, and the function at x plus h is 2 times x plus h cubed plus x plus h. Now, the x plus h all cubed is a little bit more of a hassle to expand, but there are some rules that we can learn to help us out. And the rule to expand anything that looks like this, so x plus h to the power of n, where n could be 0, 1, 2, 3, follows something called Pascal's triangle. Now, Pascal's triangle starts with 1s on the outer edge, and then in between I add like 1 and 1 makes 2. I do 1, I add 1 and 2, I get 3, 2 and 1 I get 3, and 1. I repeat, 1, 3 is 4, 3, 3 is 6, 3, 1 is 4, 1, I'll do it one more time, 1, 5, 10, 10, 5, 1. Now how this works. If I have n equals 0, I'm looking at the top line, n equals 1, the next line, n equals 2, third line, n equals 3, the fourth line, n equals 4, the fifth line, and n equals 5 being the sixth line. When n is 0, I get x plus h to the power 0. Anything to the power 0 is just 1, and so we're left with 1. When n is 1, I get x plus h to the power 1. I don't need to do any special rules there, that's just x plus h, which is like 1 times x and 1 times h, or the 1 times x and 1 times h. X plus h to the power 2 is, we know that this is x squared plus 2hx plus h squared. Where that comes from is I have 1 times the first variable to the highest power that we can get, then 2, and we introduce the next variable, and we decrease the previous one by 1, and 1 times I remove the x, or I decrease its power by 1, but that makes it 0, and I increase the h by 1 to get h squared. So x plus h to the power 3 is, if I look at our formula, we've got 1. So that's 1 times x cubed. And then I've got 3. That's plus 3 times, I'm going to introduce the next variable and reduce the power of the x by 1, plus 3. I'm going to increase the power of the h by 1 and reduce the power of x by 1, plus 1. I'm going to reduce the power of x by 1 more to make it gone, and increase the power of h by 1 to get h to the power 3. And that is how we expand this without doing any extra steps. I'll also show you the power of 4. So we have 1 times x to the power of 4 plus next variable is 4. So 4, introduce the h, reduce the x power by 1 to get to 3, plus 6. Increase the power of h by 1 and reduce the power of x by 1, plus 4. Increase the power of h by 1 more and reduce the power of x by 1, plus 1 times. Increase the power of h by 1 to get 4 and reduce the power of x by 1 to get 0. So applying this to our question, we now have 2 times x cubed plus 3hx squared plus 3h squared x plus h to the power 3 plus x plus h, which we can then expand to get 2x cubed plus 6hx squared plus 6h squared x plus 2h cubed plus x plus h. Putting that all into the formula from before, we'll get f dash x equals a function of x plus h, so that is 2x cubed plus 6hx squared plus 6h squared x plus 2h cubed plus x plus h minus, in brackets, 2x cubed plus x, all divided by h. We simplify, so 2x squared minus 2x squared and the x minus x. When you do this, all the terms with h's should always subtract away. Leaves us with 6hx squared plus 6h squared x plus 2h cubed plus h, all of h. Something I always forget is to write limits. So f dash x equals limit as h approaches 0, limit as h approaches 0, f dash x. Now we can divide the h's. We still haven't applied the limit, so that still needs to be there. We get 6x squared plus 6hx plus 2h squared plus 1. Now I'm going to apply the limit by making h 0, and I get 6x squared plus 1. That is how you differentiate from first principles. It doesn't use any differentiation rules apart from rise over run. And it gives us this function, f dash x, which when you plug in any x value will tell you the gradient at any point.